On July 4th, 1997, after a journey of 7 months across 200 million miles of space, the craft known as Mars Pathfinder successfully reached its final destination. The primary goals of this mission were to provide a low-cost delivery system for placing payloads on the Martian surface and to deploy a new kind of robotic mini-rover. This program profiles the tremendous successes of the Pathfinder spacecraft, specifically made for Mars. The Pathfinder's predecessors were the two very expensive and highly complex Viking probes that landed on Mars in 1976. The Viking program was one of NASA's boldest and most expensive efforts to systematically investigate the planet Mars. These twin probes first orbited, then detached landers that descended for a soft landing on the Martian surface. Based on a variety of atmospheric and soil analyses conducted by the Viking landers, scientists were able to conclude without question that meteorite samples found on Earth several years ago originated from Mars. Scientists theorized that a comet or asteroid impacted on the Martian surface millions of years ago and ejected rocks into space that ultimately landed on Earth. One of the most significant discoveries in the history of humanity came on August 6, 1996, when NASA scientists studying these meteorite samples found both organic molecules associated with life forms and actual fossilized remains of life. Their findings were subsequently confirmed by other scientists in Europe. A primary task of any future probe sent to Mars will be the search for water and some sign of life. The Pathfinder is one of the first of such pioneering probes introducing the new Millennium Program, an innovative series of unmanned missions to systematically explore Mars and other parts of the solar system. These probes will utilize smaller, faster, cheaper spacecraft designed with narrowly focused scientific goals and built quickly enough to take advantage of the latest available off-the-shelf technology.
NASA is undertaking a revolution driven by the information age. It's allowing us to build our spacecraft much smaller, much lighter, and so much less expensive, and also to be much more productive. And this is going to allow us to do much more science. In the past, we'd send a probe to Mars every decade. We are now planning on sending 2 probes to Mars about every other year when the launch window opens up.
The Mars Pathfinder mission, built and managed by the Jet Propulsion Laboratory, or JPL, a NASA facility, was created to test new technologies and engineering designs. The Pathfinder's innovative and cost-effective 3-in-1 spacecraft with an entry, descent, landing package houses a lander that includes a high-tech rover tucked inside. JPL designed the Pathfinder lander with the ability to survive the harsh conditions of the Martian surface for at least 30 days, while the rover was configured to provide a week of safe roving. The Pathfinder is a relatively small spacecraft, weighing about 850 kilograms or about 1,870 pounds. The lander itself weighs only 300 kilograms or about 660 pounds, less than half the weight of a Viking lander.
The nice thing about these missions is, in order to be cheap, they're small. And they launch on small launch vehicles, and they don't cost very much. So, for example, Pathfinder and Mars Global Surveyor are launching on Delta launch vehicles, which are much smaller than the launch vehicles that have been used previously. And in fact, they've never been to a planet before, so it's going to be a first for going to Mars for the Delta, or launching a mission to Mars with the Delta.
In addition to that, the launch vehicles that it takes to launch these missions are much, much less expensive. Rather than costing, say, $300 or $400 million to launch a spacecraft because it is very large and massive, we can launch a spacecraft for perhaps $35 or $60 million. So the launch costs also are dramatically reduced with the smaller missions.
Viking landed in 1976, and in today's dollars, Viking would cost $3.6 billion if we had done it today. Mars Pathfinder cost about 6% of Viking. Each one of our missions now is down to the cost of a major motion picture. Pathfinder project is basically about getting this system to Mars and operating it on the surface of Mars. Pathfinder is an experiment in low-cost spacecraft, in low-cost space missions. It's going to be the first of the new generation of low-cost missions that JPL has done. And next to NEAR, which is the Near-Earth Asteroid Rendezvous being built by the Applied Physics Laboratory on the East Coast, it's going to be the second Discovery mission launched. Now, Discovery missions are for the express purpose of doing science within a low budget. And so when we get to Mars, what we're going to be doing is demonstrating that we can actually go to Mars and land on Mars for a small fraction of what it cost us to do it the last time.
JPL was successful in designing and building the Mars Pathfinder with a direct descent lander that was able to place the payload safely on the surface without first having to orbit. This novel method of diving directly into the Martian atmosphere worked like a charm. The Pathfinder hit the atmosphere at a speed of over 7.5 kilometers per second. Parachutes then deployed to slow the descent of the landing package. Three small rockets fired right on time to further slow the craft. Then giant protective airbags inflated around the probe in much the same way that airbags work in passenger cars. As the probe closed in on Mars, it jettisoned the parachutes and bounced onto the surface like a huge ball, rebounding as high as a 10-story building. It was calculated that the spacecraft bounced 16 times across the landscape before coming to a halt. The airbags performed perfectly and sustained little or no damage. To top it off, the spacecraft landed on its base pedal, allowing it to communicate its successful landing to a jubilant team on Earth only 3 minutes after touchdown.
I think we might have a phone call.
Hello, Mr. Vice President.
Hey, Dan. Congratulations to all of you out there on behalf of President Clinton and all of the people of our country. Happy 4th of July, and congratulations on doing an absolutely outstanding job.
Well, I tell you, I'm here with the Deputy Project Manager and Ed Stone, the Director of the Jet Propulsion Lab, and I can't begin to tell you what a wonderful job these people have done for our country.
After it was determined that the spacecraft had successfully landed intact, it took several hours for the airbags to deflate and retract.
And then Pathfinder opens up like a flower, and there's a rover sitting on one of the pedals. A little rover this big, like the one that's behind me. It's a full-scale model.
Pathfinder landed within 20 kilometers of the targeted landing site. The exact landing coordinates in Aris Vallis, the valley where Pathfinder landed, were later identified as 19.33 degrees north latitude, 33.55 degrees west longitude. The Pathfinder rover, called Sojourner, has accomplished a revolutionary feat on the surface of Mars. About a day after landing, the Sojourner rolled off the pedal on its historic journey. For the first time, a robot equipped with sophisticated laser sensors and automated programming is thinking and reacting to unplanned events on the surface of another planet.
There are many challenges in exploring space away from Earth, and one of the challenges is the great distance. The signals coming back to us are very, very faint because they have to come over such great distances. And the time it takes for the signal to get here means that we cannot sit here on Earth and control in real time the spacecraft or the rovers on the surface of Mars. Typically, Mars is on the order of 10, 15 minutes one-way light time away, and it varies throughout the orbital year of the Earth and Mars.
But there's always a time delay from Mars, because Mars is so far from the Earth. Radio signals travel at the speed of light, and so by the time your rover is going to fall off the cliff, if you said, "Stop!" the rover would already be over the cliff. So you have to have a lot of autonomous control on your robotic vehicles.
So you can no longer expect to interact directly with the spacecraft in real time. You have to have smart enough spacecraft that they can take care of themselves between the phone calls that you can manage to you could connect with them.
The rover's probably only going to be able to send information to Earth or get information from Earth a few times a day. And that means that 3 or 4 times a day, or maybe only once a day, you actually get to tell the rover to do something. The rest of the time, it's got to be doing it on its own. And so this is going to involve a high degree of autonomy. And the more autonomy you can give it, the more it will be able to get done.
The Pathfinder's distance from Earth and the harsh surface conditions of the planet presented unique equipment performance and survivability challenges for its designers.
On Mars, it's very cold at night. One of the tricks to a Mars lander is to keep things from freezing to death. And so the electronics have to be shielded, and so we're working on thermal protection technology. Like the rover behind me has what's called a warm electronics box, which is a double-walled thermos bottle, and all the electronics are inside there. And during the day, we run the computers and the heaters and warm everything up nice and toasty. And then at night, the rover goes to sleep, and the temperature drops, but it doesn't drop so much that it freezes the electronics. Sun comes up the next day, the solar panels start generating electricity, and we warm up again. The
Pathfinder lander, later renamed the Carl Sagan Memorial Station, sent back tremendous amounts of information on the thin Martian climate and wind. Temperatures vary from highs of about 0 degrees centigrade to lows of about minus 70 degrees centigrade, with a light breeze of normally 6 to 8 kilometers an hour. In an effort to accomplish as much science as possible during this mission, NASA welcomed participation from other countries involved in planetary exploration in order to establish international scientific experiment packages on both the lander and the rover. The Mars Pathfinder was a groundbreaking step in a new era of international cooperation, as many countries contributed to the weather station and science projects in addition to providing their expertise in designing the experiments themselves.
You might remember that the two Viking landers, their drawback really was they had an arm. But the arm, as it always is with arm, the arm was just too short to reach interesting rocks. And actually, that's why we developed in ESA the idea that you have to have something different. You have to have a kind of instrument, we called it instrument deployment device, which brings the instruments which have to get into contact with the rocks to the rocks.
The rover sensor was designed with the ability to measure the composition of rock and soil surfaces with which it contacts. The rover's analysis of several rocks, given unique names such as Barnacle Bill and Yogi, among others, revealed both volcanic and sedimentary rocks throughout the landing site with many different minerals, including aluminum and magnesium. This information will help answer questions about the composition of the crust and evolution of the climate on Mars. Upon the official end of the 30-day mission, both the Pathfinder lander and rover were still healthy, with the rover clocking over 52 meters distance and taking over 385 spectacular pictures of rocks and the lander. In this new era of international cooperation and collaboration, the information sent back from the surface of Mars was made available to the world internet community nearly instantaneously.
Being a different kind of program, I was here in the spring, and a young man, Kirk Goodall, came up to me and said, "Dan, we can't be on the internet because we're going to get too many hits." He said, "I'm concerned because we only have a capacity for 5 to 10 million hits here at JPL." So I authorized him so that every person in America who wanted to turn on to the internet to watch this mission could do it. And he informed me we now have a capacity somewheres between 75 and 100 million people to tune into the internet, and they told me that by about 5 or 6 o'clock today, they anticipated 40 million hits. This is exciting. We are now really in the electronic age, and I'm so proud that we could get this information to everyone who wants to see it.
All of our pictures, as soon as we get them, will be available on the internet. And they'll be available on real time on NASA Select TV, so you can turn in your cable channel and see the latest from Mars. We'll have Mars weather reports. We're going to try to get weathermen giving the weather report from Mars every day. You know, cold, cold and windy, dusty today, not dusty today. We found some water today, and things like that.
Virtual reality is not really a technology of the future. Virtual reality is a technology of today. Virtual reality is simply a way of rendering information, of making information more user-friendly, basically, by giving you a sense of presence in a remote environment. So that's one aspect. Another aspect is in making the terrain seem real to other people, the public. Again, you can put virtually anybody on Mars in virtual reality.
Preliminary analysis of the Pathfinder mission confirms that at one point in Martian history, the climate was wet and warm with huge oceans and rivers like those on Earth. Conditions such as this were certainly favorable to the evolution of life. At present, Mars is a dry and dusty desert with no sign of life. The scientific data collected by the Pathfinder mission may prove to yield invaluable information detailing how this change occurred. Although this mission was not specifically designed to search for life on Mars, scientists remain hopeful that future analyses of the data collected by the rover will produce clues confirming the existence of organic molecules and life forms such as those found in the Martian meteorites on Earth.
We're really trying to understand Mars. We're trying to get to where we can know Mars so well that we can understand several things. One is, was there ever life on Mars? Because we know Mars was warm and wet. At about the same time the Earth was first evolving life, Mars had conditions that could have evolved life as well. And if it did, that means that there are now many broader range of places, a much broader range of places where you can expect to look for life. So it has profound implications for life in the universe.
The only approach we can take to understanding how sophisticated life on Mars could be if it ever arose is by comparison to the Earth. If you look at the record of life on Earth was microscopic, just bacteria and algae, for almost 2 billion years. And on Mars, if there was life there, it would not have been around for that long. So just by this very simple comparison, what we're expecting is that on Mars, life would never have gone beyond the simple microbial single-celled stage.
And maybe we could find fossilized life on Mars. This would be an unbelievable breakthrough in human understanding, just to know that at some point in time, life might have existed, even at a very low form, in a place other than Earth.
I would think life on Mars, if it ever evolved, it started out probably from the same precursor molecules. If you have carbon, if you have water, if you have nitrogen, if you have oxygen, you form amino acids, you form a number of precursors, molecules for life. It would be somewhat surprising if one would have had on Mars similar conditions as we had on Earth, say 4 billion years ago, and life would not have developed there.
Searching for life on Mars is going to be a challenge because not only do we have to find a place on Mars where life could have survived, but more importantly, we have to find a place on Mars where fossil evidence of that life would be preserved. And that's the challenge, finding an environment that would preserve evidence of life.
The information gained from this Pathfinder mission will provide added direction to future Mars missions in this decade and into the next century. Future landers will capitalize on the Pathfinder's scientific, engineering, and technological experience.
In terms of how rovers are going to have to operate on Mars in 2003, 2005, whenever we put them there, they're going to have to be a lot more autonomous than we currently have made them. Now, I don't think the limitation is actually the computers in terms of the processor of the computer. I think the limitation is having actually written and demonstrated the software that the computer runs. I mean, it's really an issue of developing computer software for autonomous operation, and that really does need to be done.
In the hunt for fossilized remains on Mars, future probes will begin a promising search in dry lakes or riverbeds, as well as near the poles where significant amounts of water still remain today. Some scientists suggest sending probes to dig beneath the planet's surface to search for life forms accessing underground water where they are protected from the sterilizing effects of intense solar radiation. These landers will use Pathfinder's centralized system architecture, employing new microelectronics and lighter materials to reduce size and volume, resulting in smaller launch vehicles and reduced mission costs. The main mission goal, however, will be focused on the search for life on Mars.
You can imagine if you want to explore another planet like Mars, that you need to get down to the surface of Mars in more than one or two spots. You can't imagine understanding the Earth from having landed on the Earth in just one place. It's much too complex a planet. Mars is equally complex, and we need to find a way to systematically go back to Mars every opportunity there is with a series of small probes that can land on the surface, eventually drill down beneath the surface, looking for water, looking for any other evidence of the early era, left from the early era of Mars, when there was lots of water on its surface and where simple life forms could well have evolved.
In 2001, our lander is going to be landing in the ancient terrain of Mars, hopefully near an ancient lake bed. So we'll be able to see if there was ever, maybe, be able to see if there was ever life on Mars. In 2003, we hope to go with the Europeans on a project called Inter-MarsNet, where we'll be landing maybe 3 or 4 landers, and the Europeans will be providing an orbiter for a communication relay. And then in 2005, we're going to try to do a sample return, bring a piece of Mars back to the Earth.
Certainly one of the main themes has to be looking for clues as to the origin and evolution of life in the solar system. That is, looking for fossil evidence on Mars, or bringing pieces of Mars back so we can examine them here on Earth, to look for fossil evidence of life that might have evolved on Mars. Looking up near the polar regions where there still is frozen water ice, which may mean that there's a possibility there might be some residue, a life residue from that earlier era.
I think if life was there, it might be not too difficult to find evidence for it. It's much more difficult, in fact, to prove that there was never life on Mars. Because we can always say, okay, we just didn't look at the right spots, we should have gone somewhat deeper, or we should have gone more towards the poles or more towards the equator. So to prove that there was really never life on Mars is much harder.
Now we have a planet that had an ocean which is gone. that must have had glaciers, enormous atmosphere, flowing water, and it's all now a gigantic desert. That's a sobering lesson of planetary evolution, but it's also far better than human imagination could ever have hoped for. And I've said it before, I don't know if there's any life in the solar system except possibly on Earth, but imagine that someone were to return with a robotic spacecraft a fossil acorn from Mars. And imagine what that would do to our imaginations and our children's imaginations.
We need to understand exactly where we want to land, because the rovers aren't going to be able to go 100 kilometers. They might be able to go a kilometer or two. And so we need to know something about where we're going to land. So that's why in 98 and 01 and 03, we want to send our landers to the interesting places, and then we can say, oh boy, we want a piece of this. So we'll go back and land there again and then pick up a piece of that. In 2005, we might have rovers go around and collect samples and put them in a box, and then in 2007, come and get the box and take it home. So we don't know really how it's quite designed yet.
There are some very key enabling technologies that sample return could be demonstrating. Getting something on the surface of Mars, a rover, and then getting something else to rendezvous with that rover on the surface of Mars. That's a key technology for human missions, because the way you're going to do human missions is you're going to land a capsule, a base, probably an opportunity before you land the people. And so the people are going to get on the surface of Mars, go to the base, you know, surface rendezvous with the base, drive a truck or whatever, open the doors and turn on the lights. That's the sensible way to do it. And it's a very similar problem to picking up samples with the rover, picking up those samples and coming home.
As the planet most widely assumed capable of supporting some form of life, the lure of Mars crosses international boundaries in an effort to better understand our universe. Mars, however, is not merely a destination, but is instead a step toward expansion of life beyond Earth.
Mars is not just of interest to Americans, but it's of interest to people around our planet. And over the next decade, there will be robotic spacecraft going to Mars from Japan, from Europe, from Russia, the United States. And I anticipate even more countries will join in, because the human spirit wants to know an open space frontier. And Mars is one of the 2 planets in our own solar system that's in the life zone.
Marzikad is a Russian-built rover. It's a 6-wheeled rover, and it's really very highly capable rover. The Russians have been excellent at their certain aspects of Russian technology that they've focused on, particularly things involving mechanical engineering. Their rover is a really very capable surface platform. The Russians plan to fly that rover, the Marzikad, in 2001. Now that actually could be the rover that's going around and picking up the samples which are brought back to Earth by a U.S. lander on a subsequent opportunity.
Right now, we're sending robots to Mars. Well, why are we sending robots to Mars? In my mind, we're sending robots to Mars as scouts. They're going to check it out so that that can be followed by humans. Why are humans going to Mars? Humans are going to Mars to see if it could be a long-term home for life. We're also scouts. We're scouts for the broader phenomenon called life.
I would not say there will never be a man on Mars, because so far I think man has always, man and woman of course, have always done what in principle is possible. The Earth was explored up to high geographic latitudes, and the oceans were explored as far as down to the absolute maximum depths. So I'm actually more or less sure that also man will once start to go to Mars.
Common question in the space program is always the tension between, do you need people or should you just use robots? People are adaptive. When something happens, they're able to react like robots can't. They have versatility and flexibility and manual dexterity. So there are things that people could do that robots can't. But we will not send people until it's economical and the potential for scientific or economic benefit is high enough. And that's the approach we're using. Yes, we need people. Yes, we need robots.
The robotic program and the human exploration program really work together in the sense that when you send a human being to, say, Mars, which I think will happen, certainly, hopefully not too far into the next century, we would like those human beings to do the most important things they can do during their stay on Mars. That we will know because the robots will have explored Mars well enough that we know what the most important questions are that the astronauts can help us answer, and we will know where the most important places are for those astronauts to visit. So the robotic program will lay the groundwork in terms of understanding the Mars so that we can be most effective in our initial brief human explorations of that nearby planet.
As a direct result of the excitement created by the tremendous success of the Pathfinder mission, the new goal of the American space program has become focused on sending astronauts to Mars. As we have seen from the space effort made over 3 decades ago, this fresh endeavor will power another revolution in science and technology with positive fallout that boosts the economy with exciting spin-off developments and reanimates the educational system with new information and heightened interest in future discoveries. As we saw in the 1960s and 70s, national morale and the human spirit are direct beneficiaries of such magnanimous accomplishments.
When we get to human missions, it's almost certain we're going to have an international endeavor, just like International Space Station Alpha. I mean, that's got Europeans, it's got Japanese, it's got Russians, it's got U.S., and I think that's the way we'll be going to Mars with people.
Any serious effort to land a manned mission on Mars would no doubt cost several $1 billion and thereby raise an important question as to whether the benefit of such a mission would be worth the cost. Perhaps the most compelling reason to go to Mars is the distinct possibility that life may have existed or may still exist there.
A lot of people talk about going to Mars and living there because there's this association that maybe there was once life on Mars. The difficulty with that scenario is that currently it is much more difficult to get to Mars than it is to get to the moon. You have to travel for a much longer time. When you're there, you are basically isolated from everybody else for a period of 2 or 3 years. It's like the global voyages of Magellan. You don't see home for a long time, and nobody can help you.
By about 2018, we hope to be able to field a human mission to Mars. We haven't actually worked out the details, but 2018 is a nice time frame because you've got the space station that's going to be operational in a few years. People need to live and work on the space station for a while to see how much zero gravity they can stand, and they need to be able to understand something about partial gravity.
There are several areas in which I think we need to look at closer before we talk about making a long trip to Mars or before we talk about living for several years out in space as we make this trip. And that's, we need to look at radiation effects will be a big thing. We also need to look at the calcium loss in the bones, and we need to look at the cardiovascular system to make sure that after an extended period in weightlessness, the cardiovascular system will rebound and your heart will function properly when you get into a gravity situation.
We need better rockets to get us to the space station economically, and those same rockets can be used to take us to Mars. So by 2018, we ought to have the technical infrastructure in place and a sufficient understanding of Mars so that we know how to send people there.
I can't think of anything worse than making a great trip out to Mars, and you spend a year or whatever getting there, and then you land and you say, great, here we are, we've got human beings on Mars, and then they can't get up and walk around and explore, So that's where I think a lot of the life science research is directed, is to make sure that when we do land on Mars, that we'll be able to live and function there.
Within 20 years or so, if Mars turns out to have resources that we can use, we ought to be able to start building up settlements and actually starting to settle the planet and learning to live there. So I think in 50 years, if we find out the technology base and we do everything carefully, we ought to be able to get there.
So you have to have a highly reliable technology that's failure-free or repairable, that you've searched every contingency so that you don't die while you're there. And then under those circumstances, you can live on Mars, and there's some advantages because there's an atmosphere that has a lot of carbon dioxide and little of anything else, but you can do things with it.
Now on Mars, we know there's water because we can see the polar caps. And the water, in fact, when Viking did an analysis, they found that the dirt was full of water. In fact, it was so full of water it saturated their instruments, so we don't know how much water there is. But water has been somehow absorbed into the soil. And so there's water, there's oxygen can be made out of the carbon dioxide in the atmosphere. Oxygen can be gotten out of the rocks because we know they're iron oxide. And so you got water and oxygen, and you can put out solar arrays because it's reasonably close to the sun, so you can use solar arrays feasibly. And so you've got power and oxygen and water and dirt. What else do you need? Now, you don't have that anywhere else in the solar system except on Mars.
If we could find ways of living off the land on Mars, if we could find resources there to make value-added materials and resources to live, economic resources to bring back to Earth, we could then perhaps think about 50 years from now, transitioning into sustained human presence.
It has been said that knowledge is power. The knowledge we stand to gain from the Pathfinder mission has the potential to unlock the secrets of Mars and thereby provide bold, new opportunities. We as a people have the power to shape our destiny, a destiny that may find humanity as settlers of the space frontier.
Perhaps there's water on Mars. We could convert that into a very high-energy fuel, hydrogen and oxygen, and we could also have water to drink. We could have oxygen to breathe. We need to take seeds with us and not foodstuffs, because foodstuffs are very heavy. So we'd like to be able to learn how to plant foodstuffs on Mars in the Martian soil, in the Martian environment. And then we'd like to figure out how to have what's called a regenerative life support system, so that we could recycle the air we breathe and we could recycle the water we drink, so we don't have to constantly take a lot more with us. If we could overcome these issues, we're on our way to Mars.
There are very strong philosophical reasons for moving to space, to learning how to use resources off the Earth and prepare ourselves for extraplanetary living. But you have to face up to the practical problems of garnering the resources, which are immense, in order to do this exploration. And you also have to have organizations and institutions that are responsible enough to use those resources wisely so that the public trusts them in their use of their expenditure of large sums.
There's a question I get asked many times. Why should the general public be interested in NASA exploring Mars, other bodies in our solar system? It's not NASA's program. The program belongs to the American people. NASA is about the future. NASA is about understanding our universe and solar system to better understand our own planet. We have to look out into the future for the next generations. And NASA is one of the few things our society does that reaches out 10, 20, 30, 50 years.
The United States is a spacefaring nation. We have a whole variety of systems in space now, which will be there, a part of our everyday life. The purpose of an agency like NASA and a laboratory like JPL is to essentially expand that frontier of human activity, to constantly move out, to do things no one else has done so that human activity can gradually expand into the full realm of space. And that is, I think, a very important part of the future of this nation.
So I think to view the Pathfinder mission followed by a sample return mission where we bring a piece of Mars back here and study it, followed probably by another sample return, rover missions, followed by humans, think of them as steps along the way. And the ultimate goal, at least in my mind, is another planet that has life. And in some small way, Pathfinder is the next small step in that journey.
The Pathfinder's discoveries both increased our knowledge of Mars and thus our own Earth history, as well as provided important guidelines for future missions. In the realm of science and technology, this small and inexpensive spacecraft paved the way to a bright space exploration future and ushered in a new era of international cooperation in pioneering the great unknown.